Hello everyone, we are Team Boat Allion. I'm Nyarazi and here are my teammates Anirudh and Varad. We are presenting on our project Transformer-Based Sensor Fusion. In this presentation, we will be covering various aspects of this project, which you can see in the overview. Autonomous robots require accurate and robust perception to operate safely in their working environments. However, fusing LiDAR point clouds and RGB camera data remains challenging due to differences in spatial resolution, data representation, sensor noise, and drift. Existing sensor fusion methods depend heavily on calibration and degrade under real-world conditions. Our project addresses this by using a transformer-based fusion approach that makes 3D object detection more robust and reliable. This project provides a hands-on way to understand how transformer architectures can be used for multimodal sensor fusion. Looking at prior work in the industry, sensor fusion has evolved significantly over time. Early approaches followed classical lead fusion, where each sensor was processed independently and combined using techniques like Kalman filter, often leading to loss of useful information. More recent transformer-based methods such as BEV format introduced spatial and temporal queries to project multi-view camera features into a unified bird's eye view. Another paper, BEV fusion, further advanced this idea by introducing separate encoders for LiDAR and camera data while fusing them in a shared BEV space. Bharat will explain more.
Transfusion is a robust sequential transformer-based framework for LiDAR camera 3D object detection that uses a soft association mechanism. The model has two convolution backbones, a 3D LiDAR backbone that extracts BEV features from point clouds, and a 2D camera backbone which extracts image features. The detection head is a two-layer transformer decoder where the first layer produces initial 3D boxes from LiDAR-based object queries. The second layer fuses these queries with image features through cross-attention for robust multimodal association. The transfusion paper used Newscene's dataset for their model. The Newscene's dataset was available in 10 batches of multiple 20-second long scenes, each with approximately 40 annotated keyframes. Each keyframe includes an image from 6 cameras and a LiDAR sensor image. Originally, our project had planned to cater to indoor ASR systems, and the best platform to simulate this was Isaac Sim with the R2B dataset, which provided approximately 15 to 20-minute long Rosberg recordings of various indoor spaces. We created an environment in Isaac Sim and imported the Segway Nova Carter robot, which was used to collect the R2B dataset. However, this setup would not properly work given our scope and timeline. Firstly, the R2B dataset is very ROS dependent and limited, requiring a lot of data processing time, which would take time away from the core project. Isaac Sim itself is notoriously GPU intensive. Even with a 5070 Ti setup, training and simulation would take multiple days. This is when we decided to go back to Newscene's dataset so we could focus more on the transformer architecture. The main challenge was the code base provided by the authors, which was completely obsolete and buggy. It ran on older PyTorch and CUDA versions that would not properly work with latest hardware. The detection framework and the MMCV toolbox was fantastic discoveries for us. They provided much easier data processing APIs, so we did not have to write them up from scratch. To run this project on our system, we first upgraded the codebase to PyTorch 2.7 and a newer detection library, which allowed us to use the Hungarian assigner 3D function for optimal 3D box matching. We made several improvements to the original transfusion pipeline as well. First, we replaced the VoxelNet LiDAR backbone with a pillar-based one, which avoids expensive 3D convolutions by projecting the point cloud to a 2D pseudo image. We also updated the activation function from ReLU to GELU for smoother gradients and better handling of negative inputs in transformers. This also avoided dead neurons as it allows small negative values and maintain a small non-zero gradients in the negative range. To stabilize training with smaller batches, we switched from batch norm to layer norm and enabled automatic mixed precision to reduce memory usage and speed up training.
For our experiments, we use the pedestrian-focused Newscene's mini dataset. Single GPU training imposed strict memory limits. By introducing AMP, we reduced VRAM usage by approximately 30 to 40%. This allowed us to double the batch size and reduce training time from 150 to 105 minutes for 6 epochs. We looked at the gradient norm to understand the training stability. AMP introduced instability as observed with the sharp spikes due to reduced numerical precision. After replacing ReLU with GReLU, and batch norm with group norm, the gradients became smoother and more stable, indicating improved gradient flow. Next, we analyze the classification loss, which improved after replacing ReLU with GLU, yielding smoother and faster convergence. The largest gain came from switching from batch norm to group norm, which is more reliable for small batch sizes. Finally, we examined the meshed IAU between predicted and the ground truth objects. Meshed IAU shows a consistent and upper trend, indicating improving overlap between predicted and ground truth boxes. This confirms that the model is learning accurate spatial localization in addition to correct classification. Next up, the validation metric analysis. Here we observe that particularly for pedestrian class, group norm variants show promise with shorter training below the standard ND score, which aggregates MFP with true positive metrics. Through the improvements, we were able to outperform the baseline, thus training such a huge model stable and efficient. But what do all these graphs mean? Let's see how it correlates with qualitative performance. Here is just an example how multiple cameras and LiDAR do come together in a 3D projection. This example is from a test set in a daytime scene using the LiDAR only pipeline. Some pedestrians were missed from detection as there were too few points for detection and classification, but in the LiDAR plus camera pipeline, those same pedestrians were captured. This basically shows how the camera adds more semantics such as sparse objects can be detected. Here we tried the same thing with nighttime scene. Many pedestrians were not detected when just LiDAR was used, but when we introduced the camera to the pipeline, they were detected. This makes the detection pipeline more occlusion robust when we have LiDAR plus camera.
The broader impact of this work is demonstrating that transformer-based multimodal perception can be explored effectively without large-scale compute resources. Our findings show that careful engineering, such as mixed precision training and appropriate architectural choice, can significantly lower the barrier of experimenting with advanced perception models. That said, our work has limitations. We trained on an outdoor dataset rather than an indoor warehouse dataset. And the new scenes mini dataset limits achievable accuracy and increased metric variance. Future work includes training on the full new scenes dataset, integrating data from indoor simulators such as Isaac Sim, and evaluating multi-GPU scaling. Ultimately, this project provides a practical foundation that others can build on for robotics perception research under constrained settings. And with this said, we end our presentation. Thank you for watching.